Welcome back to laser technology session. So in the last session we have discussed about the line shape function. So the atom is associated with the line shape function. That means whatever the incident frequency, it cannot take all the photons. So it have your excited state lifetime having a fixed lifetime or having a finite lifetime that will associate with the certain line width. Okay, so now from that, in the last session we measured like how the stimulated emission per unit volume per unit time. So the equation we took previously, which was derived, so your dN2 by dt of the stimulated emission is equals to minus the transition from state E2 to E1. So that we have associated with the Einstein coefficient minus B21 U of omega N2. So now your line shape function is associated with it. So that means not all the photons can be absorbed. You have to incorporate your g of omega d omega. So it becomes now minus integration b21 u of omega n2 g of omega d omega. Now I'm assuming your b21 in the Einstein coefficient is constant. So in this case you can take out your b21 and n2 out of the integration. So now your dN2 by dt, the rate of stimulated emission, is equals to minus b21 n2 integration of u of omega g of omega and d omega. That means it will be depending upon incident radiation and the line shape function. So that the rate of stimulated emission depending on these two factors. So now we will see, we consider different cases. In the case 1, your incident radiation is broadband. In the case 2, your incident radiation is nearly monochromatic. So how the rate of change of your stimulated emission will come into the picture. Now the first case 1, your incident radiation is broadband. Okay, so now I'm plotting intensity versus frequency. Your incident radiation is quite broad, so that your incident radiation is your u of omega. If atoms are interacting with the broadband incident radiation compared to your line shape function, that means your line shape function is g of omega. Now you see your incident radiation is quite broad and the red curve is your g of omega. That means the atom can absorb only the photons within this region. That means that your dN2 by dt equation, that means your transition from state E2 to E1 will accordingly changes. So that means our interesting region is g of omega, because that is the only number of atoms can excite to the excited state. So we integrate over this region. So in that region your g of omega is appreciable compared to your u of omega. So at this point your u of omega is essentially a constant. We can take out from your integration part. So now your dN2 by dt, the rate of change of your stimulated emission, is equals to minus b21 n2 u of omega integration of g omega d omega. And we know that your line shape function over the whole area, so your g of omega d omega integration over, that gives you, that's 1. So that means that's a total probability should be equals to 1. So your dN2 by dt equals to minus b21 n2 u of omega. So this is consistent with our previous result, which is derived from our red equations. So that is equation number 3 if you refer back. So this equation represents the rate of stimulated emission per unit volume when atom is interacting with a broadband radiation. So we call broadband, it means it has a number of spectral lines at different frequencies. Now if you see, it ranges from almost at this frequency to and this frequency. It has that you have many range of frequencies in the spectrum, those spectrum you call a broadband radiation or a broadband spectrum. So now with the broadband radiation is your input, then your rate of your stimulated emission rate will be this one. Now if your incident radiation is nearly monochromatic, so now the other case, your incident radiation is nearly monochromatic around a frequency omega prime compared to your g of omega. Now if you see your g of omega, your line shape function is this one, and compared to your g of omega, your incident radiation is nearly monochromatic. Now how about your stimulated emission rate? So that is equals to minus B21 N2 integration of E of omega, G of omega, d omega. Though you have atom has a distribution of G of omega, but you don't have those number of frequencies in your input radiation. So your input radiation is nearly monochromatic. So that means only this region, only the U of omega region is your region of interest. So your G of omega at this region is almost constant, so you can take out from the integration. So your equation becomes minus B21 N2 G of omega prime, so I am taking at the frequency of omega prime, integration of U of omega d omega. Integration of U of omega d omega, I will take it as a U. So now your final equation becomes dN2 by dt of your stimulated emission is equals to minus B21 N2 G of omega prime and U. So where U is energy density of incident nearly monochromatic radiation. So the units becomes energy density per unit volume, where your U of omega is energy density per unit volume and per unit frequency interval. So that is the difference between your U and U of omega. So now when atom is described by line shape function G of omega interacts with a nearly monochromatic radiation at frequency omega prime, this equation 11 becomes the stimulated emission per unit volume. So that means whenever you are considering your rate equation for the stimulated emission, you have to choose this whether your incident radiation is monochromatic or your incident radiation is broadband. So depending upon the incident radiation, you will select either equation 11 or the previous equation which is shown in the when your radiation is broadband. Stimulate absorption, or we can call absorption. Okay, now the same thing what happens when your incident radiation is nearly monochromatic. So that is same U of omega is nearly monochromatic compared to your line shape function. So now we can calculate for the stimulated absorption rate. So your stimulated absorption rate is B12 N1 U of omega G of omega and d omega. So or the region of interest, so that is only your U of omega can only be excited. So then you can take out your G of omega out. So again you get the same function with B12 Einstein coefficient. So the only change is your Einstein coefficient. The remaining whole thing is the same. So now your rate of change of stimulated absorption equals to B1 to N1 G of omega prime U. So where U is your energy density per unit volume and U of omega is energy density per unit volume and unit frequency interval. So now this equation will tell you when the atom is described by line shape function G of omega interacts with nearly monochromatic radiation at frequency omega prime. So this equation becomes a stimulated absorption rate per unit volume. So now we move on to, let's see, now we interact with the medium. Okay, so now I'm taking a nearly monochromatic source of energy density U at frequency omega prime, allowed to pass us through the collection of the atoms. Okay, so now we can see, so when the intensity, your radiation is passing through, that means your source has certain intensity. So we generally calculate your radiation in terms of intensity. So the rate of change of intensity of the radiation as it passes through medium, we can calculate. So now I am considering the medium, the plane 1 and plane 2, which are having an area of A, and they are at different positions. These planes at position at G, and this is plane 2 at G plus dg. They are separated by distance of dz. Okay, so now your incident radiation, it's a nearly monochromatic radiation. It's passing through your volume of the region, this region. Okay, so I'm considering front end and the back end of the planes. So now this is our nearly monochromatic light source having a frequency of omega prime, and the direction of the beam is towards this direction. So now the net amount of energy entering the volume Az, so where is A, and the volume component is with the distance dz between plane 1 and plane 2. So now the rate of change of intensity over the volume of A dz, so that is nothing but I of z minus I of z plus dz into your volume component A dz. So then I can rewrite this one. So I of z plus I of z, and this is nothing but your rate change of the intensity at the distance of dz. That means the change can be written as di by dz. Okay, so this is the intensity change with respect to this dz distance into your volume component A dz. So this is the rate of the change of the intensity through this medium. So your Iz and Iz will get cancelled. So your resultant will be minus di by dz A dz. I am numbering this is equation number 13. So now which is equal to net energy absorbed by atoms in the volume A dz. So this intensity, whatever the change in intensity, which should be equals to, because the medium is absorbed. Okay, so that is why I am talking about here. This expression is nothing but the total energy is absorbed by the atoms in the volume of A dz. So that is the rate of the change of the intensity. So this can be happened. So you have to consider either it might be stimulated absorption. This plays a role here, as also your stimulated emission and spontaneous emission. So these three can play a role, because these are the process can happen when a medium is exposed to radiation. So the stimulated emission component is dN by dt, the rate of change of the atoms in the ground state belongs to your stimulated absorption, with the volume component Az and its incident frequency or energy. We are talking about total energy, that is h omega prime. For the stimulated emission, the rate of the change of the stimulated emission, the volume component and the energy component. Now I am neglecting here the spontaneous emission component. The reason is the energy appear from this is general. Your spontaneous emission will be broad frequency range, which also emits in all directions. So now I am talking about only omega prime frequency. So the component from the omega prime frequency for the spontaneous emission is less, and also in the propagation direction of G direction, the amount of the stimulated emission along the G direction is very less. Okay, that is the reason I am neglecting the spontaneous emission component. So now I am calculating the net energy absorbed by the atoms in the volume of A dz. So now you have the two contributions, that is from the absorption or a stimulated absorption, and a stimulated emission with the volume and energy range. So these are the two equations we already derived when the nearly monochromatic radiation is incident on a system. Then this is the rate equations we got, and now I am substituting those rate equations. For dN1 by dt for absorption is minus B12 B12 N1 G omega prime U. So this is the one, and for the stimulated emission, this is the factor, your B12 N2 G of omega prime U, and your the volume component and energy component. So now I am taking B12 G omega prime and U common, so you will get N2 minus N1 minus N2 A dz H omega prime. So, and also from the equation 10, from the Einstein coefficient, your B21 or B12 is actually it's equal from the Einstein relations. So that's why I am taking your B12 or B21 is same. From this you can calculate your B21 or B12 in terms of A21. So I am substituting that factor. So you send this, this can be B12 equals to B21. That is one of the relation that I am using it here. And now you send this one this side, and you send this one this side. So you will get a B12. So that I am substituting here. And we know that A21 is nothing but 1 over tau SP, that is the spontaneous emission rate. So that I substituted in terms of A21. Okay, so that is, this is the fact term, and then G omega prime U N1 minus N2 A dz H omega prime. So I'm here H cross can be get cancelled, and one omega prime and one of the omega prime is gets cancelled. So now this term becomes pi square C cube omega prime square N naught cube tau SP G omega prime U N1 minus N2 A dz. And we know that the intensity is nothing but your energy density per unit volume per unit frequency, unit volume is into your refractive index also involved, that is by C by N naught. So that is your intensity is nothing but IVU. So that I am going to substitute here. Your C by N naught I am taking from one of this C cube, and here N naught cube, that becomes C square N naught square, and U, that whole C by N naught into U becomes I. Okay, so this not absorbed due to the spontaneous emission and stimulated emission, the number of atoms will be equals to this factor, the total term is equation number 4. Now we can equate equation number 13 and equation number 14. So your equation number 13 is nothing but your minus di by dz A dz, and your equation 14 is pi square C square omega prime whole square N naught square tau SP G of omega prime I N1 minus N2 A dz. Okay, from this I am dropping down the omega prime, so for simplicity, so we know this is for a monochromatic frequency. So your dA by dz equals to minus your A of dz, and A of dz gets cancelled. So now the resultant term minus pi square C square omega square N naught square tau SP G of omega N1 minus N2 I. So I will write down this equation as dA by dz equals to minus alpha I. So if you remember, this equation we already discussed in the early section of optical absorption. So the equation now we derived it, how this equation comes. So your alpha is nothing but your pi square, this whole term, up to here is pi square c square omega square n naught square tau sp g of omega n1 minus n2. So where when we talk about optical absorption, we call the alpha as a absorption coefficient, but here you cannot call this one as a absorption coefficient. I will tell you why in a little later. So now you see your alpha is depending upon frequency omega, so that we can also call alpha is function of omega. And this equation I showed you in the previous session in the optical absorption. This equation you can get I of z equals to I naught e power minus alpha L. So you send this dz this side and integrate over integration on both sides, you will get this equation. Okay, so this is the I of z tells you that the intensity along the g direction, as you at different position of g you can calculate the intensity, and your I naught is your input intensity, and e power minus alpha I, your alpha is a frequency dependent component. So now if we draw a plot between alpha versus omega, for example your n1 is greater than n2, that means the number of atoms or the electrons in the state E1 are much greater than n2. Okay, that means that you have the state E1 and E2. Now you have number of atoms or the electrons on the state E1 or N1, very few are in N2. So that is the condition. What happens? Your alpha of omega having peak like this function. Okay, so this is your alpha when is N1 is greater than N2. So as you see here, your N1 plays a dominant role, you can neglect your N2. So now this is total equation for this curve. So now your N2 is greater than N1, that means your N2 is dominating, so now you can neglect your N1. So that means you will get minus signature, the minus of pi square c square by omega square n naught square tau sp g of omega n2. So that curve becomes, it goes downwards, like you get the negative values. So these are all a positive axis and this will be your negative axis. So that means your n2 greater than n1, what happens, your alpha becomes negative. That is your condition for population inversion. So this gives you your amplification. So how it is amplifying? Because see, your frequency dependent of alpha almost the same as that of the line shape function g of omega. So your n2 greater than n1, your I of z becomes, this factor becomes negative because of the minus n2, your alpha becomes negative, you substitute your alpha, negative quantity into negative becomes positive quantity. So your dI dz equals to alpha I. So now you integrate on both sides, you will get Iz equals to I naught e power alpha I. So what happens, if you plot intensity versus g, it is exponentially increasing. So that means your output intensity I of z is always greater than your input intensity. That means because this exponential factor is giving the amplification. So that is your amplification is exponential amplification. Okay, so this is where the stimulated condition happens. So you create a population inversion. Because of the population inversion, your intensity will be amplified in the medium. Sorry for the mistake. So this is along G, it's not I in both cases. As your length changes, this factor will change. So this is your E for alpha z, that is, as the length changes, your absorption, for example in this case your absorption increases. If length changes, in this case your stimulated emission increases. That means you create a population inversion, you amplify the medium, your stimulated emission will be amplified. That is the reason you are getting your input in, you are giving a 4 photons, you are getting 8 photons, like it's kind of an exponential. So I cannot say like exactly 8, but depending upon the number of photons it increases exponentially. So that along with the z direction, when it's propagating through along z, it amplifies exponentially. Then we will see it cannot be done. In that case you can take infinity z, so that you can amplify the laser beam to certain extent level. So that cannot be possible. There is always a condition, threshold condition will be there. You cannot take a length whatever the way you want. That we will discuss in the later sessions.